You think aliens haven't visited Earth because they're hiding, or because governments are covering it up, or because we're not ready, or because they're watching us from a distance, waiting for the right moment. These are the stories people tell. These are the explanations that sound mysterious and interesting, but they're all wrong, not a little wrong, fundamentally wrong, because they all assume the same thing. They assume that if intelligent aliens exist, visiting Earth would be possible, that it would be a choice, that the only question is whether they want to come here. But that assumption is false. The reason we haven't been visited by aliens is not psychological or political. It's not about readiness or worthiness or secrecy. It's about physics. It's about the structure of space-time. It's about distances so large and speeds so limited and energy requirements so absurd that interstellar travel is not just difficult. It's essentially impossible. Not impossible in the sense that we haven't figured out how yet. Impossible in the sense that the universe itself, through its most fundamental laws, makes it so. Let me show you why. Start with a simple question. Where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi. The universe is 13.8 billion years old. Our galaxy alone contains 200 to 400 billion stars. Many of those stars have planets. Many of those planets are in the habitable zone where liquid water can exist. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, these are common. They're everywhere. The basic chemistry that could lead to life is not rare. It's abundant throughout the cosmos. So, statistically, life should be common. Intelligent life should have arisen many times. And some of those civilizations should be far older than ours. Millions of years older. Billions of years older. They would have had time to develop technology far beyond anything we can imagine. They should have spread across the galaxy. They should be everywhere. We should see evidence of them. Megastructures around stars, radio signals, probes, something. But we see nothing. The universe is silent. We've searched for radio signals. We've looked for optical beacons. We've analyzed the light from thousands of stars for signs of artificial structures. Nothing. No signals. No evidence. No contact. The galaxy appears empty, dead, just stars and planets and gas and dust. No one home. This is the paradox. The universe should be full of life, but it appears to be empty. Where is everyone? There are many proposed solutions. Maybe life is rarer than we think. Maybe intelligence rarely evolves. Maybe civilizations destroy themselves before they can spread. Maybe they're all listening and no one is transmitting. Maybe they exist, but we're looking in the wrong way. Maybe they're here but hiding. These are all possibilities. But there's one explanation that doesn't get enough attention. One explanation that's not mysterious or interesting, but is brutally, mathematically true. The distances are too large, the speed limit is too low, the energy cost is too high. And these facts, these physical constraints, make interstellar travel so difficult that it might as well be impossible for any civilization bound by the laws of physics. Let's start with the speed limit. Light travels at 299,792,458 meters per second. Nothing can go faster. This is not an engineering limitation. This is not a problem we'll solve with better technology. This is a fundamental property of space-time itself. The speed of light is the maximum rate at which cause and effect can propagate through the universe. It's built into the structure of reality. You cannot exceed it, not with rockets, not with warp drives, not with anything that obeys the laws of physics as we understand them. And that speed, as fast as it is pathetically slow on cosmic scales. Light takes 1.3 seconds to reach the moon, 8 minutes to reach the sun, 4 hours to reach Neptune. But to reach the nearest star, Proxima Centauri, the closest star to our sun, is 4.24 light-years away. Light, traveling at maximum possible speed, takes 4.24 years to get there. That's the absolute fastest anything can travel that distance. And that's not a journey time for a spacecraft. That's the time it would take if you were already moving at the speed of light, which you can't do if you have mass. For a spacecraft with mass, the problem is far worse. You can't reach the speed of light. You can only approach it, and approaching it requires more and more energy the closer you get. To accelerate even a small probe to 10% of light speed would require energy equivalent to tens of thousands of nuclear weapons. And that's just for a tiny probe. For a spacecraft large enough to carry living beings, the energy requirements become astronomical. But let's say you could somehow build a spacecraft capable of reaching 10% of light speed. That's 30,000 kilometers per second. Absurdly fast by human standards. fast enough to circle the Earth in less than 2 seconds. At that speed, it would take 42 years to reach Proxima Centauri, 42 years for a one-way trip to the nearest star, and that's assuming you can accelerate to that speed instantly, which you can't. Realistic acceleration profiles would add decades to the journey time, and Proxima Centauri is right next door in cosmic terms. Most stars are thousands of light years away. The galaxy is 100,000 light years across. Now think about what this means for an alien civilization trying to visit Earth. Even if they're close, even if they're only a few hundred light years away, the journey would take thousands of years at any remotely achievable speed. They would need a spacecraft capable of functioning for millennia. They would need life support systems that could sustain a crew for hundreds of generations, or they would need some form of suspended animation or artificial intelligence. And all of this assumes they can solve the energy problem. Let's talk about the energy problem. The rocket equation tells you how much fuel you need to accelerate a spacecraft. And the answer is terrifying. To accelerate a spacecraft, you need to carry fuel. But that fuel has mass, and accelerating that fuel mass requires more fuel, which has more mass, which requires even more fuel. The fuel requirement grows exponentially with the desired speed. This is called the tyranny of the rocket equation. For chemical rockets, the kind we use now, you can't even get close to the speed of light. You'd need more fuel than there is matter in the observable universe. So you need something better. Nuclear fusion, maybe. Antimatter. Even with antimatter, which produces the maximum possible energy from mass through Einstein's EHMC2, the fuel requirements are staggering. Let's do the calculation. You want to accelerate a 1,000-ton spacecraft to 10% of light speed. Ignoring deceleration, ignoring relativistic effects, just a simple Newtonian approximation, you need roughly 4,500 tons of antimatter fuel. And that's just the fuel. You also need 4,500 tons of matter to annihilate with it. So 9,000 tons of propellant for a 1,000-ton payload. A mass ratio of 9-to-1. And that's just to accelerate. You also need to decelerate at the destination. So double the fuel, 18,000 tons of propellant for a 1,000-ton spacecraft. Now consider that we've never created more than a few nanograms of antimatter in total. And it took enormous accelerators running for years to produce those nanograms. Producing 4,500 tons of antimatter would require energy equivalent to trillions of nuclear power plants running for centuries. The energy cost is not just large, it's civilizational. It's the total energy output of an advanced society for thousands of years, all dedicated to sending one spacecraft to one star. And this is the best-case scenario. This is assuming perfect efficiency. This is assuming matter-antimatter annihilation, which is the most energetic reaction possible according to known physics. Anything less efficient requires even more fuel. Chemical rockets are millions of times worse. Even fusion is hundreds of times worse than antimatter. So you have a fundamental problem. Interstellar travel requires energy on a scale that makes it prohibitively expensive even for a highly advanced civilization. And this is not a temporary problem that better engineering will solve. This is thermodynamics. This is the conservation of energy. This is the structure of physics itself creating a barrier. Now let's add another constraint. Time. Even if you could build a spacecraft and find the energy to send it, the journey takes a very long time. At 10% of light speed, centuries to millennia for most destinations. A civilization would need to commit resources for longer than most nations have existed, longer than most empires have lasted. You're talking about multi-generational projects where the people who start the mission will never see the result, where the spacecraft itself must remain functional for longer than any machine humanity has ever built. Think about our longest-lasting structures. The pyramids are 4,500 years old, but they're inert stone. They don't need to do anything. A spacecraft must actively maintain life support, propulsion, navigation, communication. It must survive micrometeorite impacts. It must shield against cosmic radiation. It must prevent system failures that accumulate over centuries. The engineering challenge is not just building a fast spacecraft, it's building an essentially immortal spacecraft. And even if you solve all of this, even if you build the spacecraft and generate the energy and commit the time, you still face the problem of what you're traveling toward. You're aiming for a star system decades or centuries away. You can observe it from a distance, but you can't see planets in detail. You can't know what's really there. You're committing enormous resources based on incomplete information. And if you arrive and the planet isn't suitable or is already inhabited or has been destroyed by an asteroid, you've spent millennia and the energy output of a civilization for nothing. This is why interstellar colonization, even for a highly advanced civilization, is not the natural expansion that science fiction portrays. It's not like European colonization of the Americas, where the journey took months and you could send ships regularly. It's more like sending a probe to another universe. The barriers are so high that even attempting it once is a civilization-defining project. Attempting it hundreds or thousands of times to colonize the galaxy is beyond consideration for any society operating under known physical laws. Now apply this to the Fermi paradox. If interstellar travel is this difficult, then it doesn't matter how many alien civilizations exist. They're all confined to their home star systems. They can't visit us because they can't visit anyone. They're stuck, just as we are, in their local stellar neighborhood. The speed of light and the rocket equation and the energy requirements create an effective isolation. Stars are not like islands that you can sail between. They're like separate universes, each causally connected only by information traveling at light speed. And information traveling at light speed is not the same as physical travel. Yes, we could communicate with a civilization hundreds of light years away. We could send radio signals. They could send signals back, but each message would take hundreds of years to arrive. A conversation would span millennia, and even that requires both civilizations to be actively transmitting and listening at the same time, which requires coordination across timescales longer than human history. This leads to another realization. Even if thousands of civilizations exist in our galaxy, they could all be isolated from each other, each trapped in their own stellar neighborhood by the physics of space-time. Each aware, perhaps, that others likely exist, but unable to make contact because the distances are too large and the speeds are too slow and the energy costs are too high. The galaxy could be full of life and still appear empty because the barriers to interaction are insurmountable. There's another piece to this, the Drake equation. This is a probabilistic framework for estimating the number of communicative civilizations in the galaxy. It multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of habitable planets where life arises, the fraction where intelligent life evolves, the fraction that develop technology capable of communication, and the length of time such civilizations remain detectable. The problem is that we don't know most of these numbers. We can estimate some. We know stars form. We know many stars have planets. We're starting to estimate the number of Earth-like planets, but we have no idea how likely life is to arise. We have no idea how likely intelligence is. We have no idea how long civilizations last, and these uncertainties span many orders of magnitude. If life is common and intelligence is common and civilizations last millions of years, the galaxy should be crowded. But if any of these factors is much smaller than we think, if life is rare or intelligence is rare or civilizations typically destroy themselves within a few centuries of developing technology, then the galaxy could have very few active civilizations at any given time, and if those few civilizations are separated by thousands of light years, they would never interact. This is the great filter hypothesis, the idea that there's some step in the evolution from non-life to spacefaring civilization that's extremely unlikely, something that filters out most possibilities. Maybe it's the origin of life itself. Maybe it's the jump from simple to complex life. Maybe it's the development of intelligence. Maybe it's the development of technology. Or maybe it's something ahead of us. Maybe civilizations typically destroy themselves through nuclear war or ecological collapse or artificial intelligence before they can spread beyond their home planet. If the great filter is behind us, we're lucky. We've passed the hard step. But if the great filter is ahead of us, we're in danger. The silence of the universe might be a warning. It might mean that civilizations that develop technology don't last long, that they face some challenge, some crisis, that most don't survive, and we're approaching that same challenge. But there's another possibility, the simplest possibility, the one that doesn't require unlikely events or catastrophic outcomes, the possibility that interstellar travel is just too hard, that the physics of the universe makes it so difficult and expensive that no civilization, no matter how advanced, regularly attempts it, that the galaxy is not empty because civilizations destroy themselves or because intelligence is rare. The galaxy appears empty because everyone is stuck at home, bound by the same laws of physics we are. Consider this. The universe is 13.8 billion years old. Our galaxy is nearly as old. If spacefaring civilizations were possible and common, the galaxy would have been colonized billions of years ago. We should see evidence everywhere, but we don't. And the simplest explanation is that such colonization doesn't happen, not because civilizations choose not to do it, not because they're hiding, but because the physical barriers are too great. The distances are too large, the speeds are too slow, the energy costs are too high, the time requirements are too long, the engineering challenges are too severe. All of these factors combine to make interstellar travel an occasional, rare, desperate act rather than a routine expansion. And if one civilization did somehow manage to send a probe or a spacecraft to another star, the chances of it arriving at Earth specifically are infinitesimal. Earth is one planet around one star among hundreds of billions. Even if aliens were exploring the galaxy, the probability that they would choose this star, this planet, at this moment in time when we happen to be here to notice, is vanishingly small. Think about the timescales. Modern humans have existed for about 300,000 years, civilization for about 10,000 years, industrial technology for about 200 years, radio technology for about 120 years. We've been capable of detecting alien signals for the blink of an eye in cosmic terms. An alien civilization would need to not only travel across the galaxy, they would need to arrive in this narrow window of time when we exist and have technology. That's an additional filter. Even if visitation were possible, the timing would need to align, and that alignment is incredibly unlikely. Now consider detection. People claim to see UFOs. They claim governments are hiding evidence. But think about what would actually be required for aliens to visit Earth undetected. They would need to travel light years, expending civilization-scale energy, surviving centuries of transit, and then hide from our detection systems. If you can cross interstellar space, you don't sneak around. You don't crash in deserts. You don't abduct people from rural areas. The technology required for interstellar travel would make any civilization so advanced that hiding from us would be trivial. They wouldn't hide. They would either ignore us completely or contact us openly. The idea of aliens visiting but staying hidden makes no sense given the physics involved. The truth is less exciting but more profound. The universe is not hiding aliens from us. The universe is keeping us apart through distance and physical law. Space is not empty in the sense that there's nothing there. Space is vast in a way that makes meaningful interaction nearly impossible. Stars are separated by distances that take light years to cross. Spacecraft would take much longer. Communication would be delayed by centuries. Coordination would be impossible. The universe is structured in a way that isolates star systems from each other. And this isolation might be a feature, not a bug. If interstellar travel were easy, if you could just hop between stars the way you hop between cities, the galaxy would be a very different place. Civilizations would clash. Resources would be fought over. The galaxy would be a battlefield. But because travel is so difficult, because each star system is effectively isolated, civilizations can develop independently. They can evolve their own solutions. They can exist without threat from others. The vast distances are a buffer. They create space for diversity, for experimentation, for life to take different paths. So where is everyone? They're where they've always been, at home, around their own stars, isolated by physics, unable to visit, perhaps aware through faint signals or statistical reasoning that others exist, but unable to cross the gulfs between stars, unable to touch, unable to meet, each civilization alone in its corner of the galaxy, looking out at the stars and wondering, just as we do, if anyone else is out there, and never knowing for certain because the universe, through its fundamental laws, keeps us separated. The silence is not a mystery. The silence is physics. It's the speed of light being too slow, its distances being too large, its energy being too scarce, its time being too long. It's the rocket equation and thermodynamics and the structure of space-time itself creating barriers that no technology can overcome. The universe is not hiding aliens from us. The universe is too big, too sparse, too bound by physical law to allow the kind of casual interstellar travel that science fiction has trained us to expect. And that's the answer to the Fermi paradox. Not that life is rare, not that civilizations destroy themselves, not that aliens are hiding, but that the universe is structured in a way that makes contact vanishingly unlikely. The distances are too vast, the speeds are too limited, the energy costs are too high, the timing is too precise. And all of these factors combine to create a universe where intelligent life might be common, but forever isolated, where civilizations exist but never meet, where we are not alone but are functionally alone because the barriers between us cannot be crossed. This is not a satisfying answer. It's not mysterious or exciting. It doesn't involve government cover-ups or ancient astronauts or imminent contact, but it's the answer that physics gives us. And physics does not care about what would make a good story. Physics cares only about what is true. And the truth is that the universe, through its most fundamental laws, has made interstellar travel so difficult that it might as well be impossible, not because we lack imagination or technology, but because space is vast and time is limited and energy is finite and the speed of light is the speed of light. The aliens haven't visited because they can't. Neither can we, and neither can anyone else. The galaxy is not a neighborhood. It's a collection of isolated islands, separated by oceans too wide to cross. And we are on one of those islands, looking out across the water, seeing lights in the distance, and wondering if anyone is looking back. They might be, but we'll never know for certain, because the universe has placed us too far apart, and that distance, enforced by the laws of physics, is absolute.